Okay, so if you recall our previous video, we found this number e, which was roughly 2.71828. It was an irrational number, and its property was that the derivative of e to the x was actually equal to itself. And the ln of x is the logarithmic function base e of x. Therefore, by definition of the logarithmic function, ln is the inverse of e to the x. And so ln of e to the x is x, and e to the ln of x is also x. And the derivative of this inverse function, the derivative of ln of x, is actually 1 over x. But there is one question left over. How did we know that e was approximately 2.71828? Right? We said that we knew there had to exist a number between 2 and 3 whose property was that its derivative at x equals 0 was 1. But how do we know x, or not x, but e, is approximately this number? Well, in this video, this is what we want to figure out. How can we estimate the value of e? All we will need to look at is the derivative of ln of x at 1. And first, look back at this equality. This is true for any positive x. So if you're replacing here x by 1, what do you have? Ln of e to the 1, but e to the 1, that's just e. So you get ln of e is equal to 1. And the ln function is a one-to-one function. So if, and this will be what we'll use, if the ln of something is equal to 1, whatever the argument is has to be e. This is the only option. The only value for which ln of that value is 1 is the number e itself. So now consider the derivative of ln of x at x equals 1. Right? So the derivative of ln of x we know is 1 over x for every x. And now we want to evaluate specifically at x equals 1. Well, this will be the derivative of ln of x is just 1 over x. So we'll have 1 over x, specifically when x is 1. So all we get is 1 over 1, which is equal to 1. But now let's find the derivative of ln of x at 1, going back to the definition of the derivative. So we know it's equal to 1. So we know 1 is equal to the derivative of ln of x, specifically when we look at x equals 1. And now let's use, or let's find the derivative, I should say, from the definition of the derivative. So we'll have to let h approach 0. We know normally we have f of x plus h, but x is 1, so this will be f of 1 plus h. So ln of 1 plus h minus f of x, but x is 1, so that's minus ln of 1. And we divide by h. And so we know this limit is equal to 1. But we also know that ln of 1 is equal to 0. Right? And here, plug in x equals 0. E to the 0 is 1, so you get ln of 1 equals 0. So now we have a rather simple limit, or at least simple looking. We get the limit, as h approaches 0, of the ln of 1 plus h over h. And I will write the over h as a multiplication of 1 over h times the ln of 1 plus h. Now the question is, well, where do we go from this point? We have to remember a few properties of logarithmic functions. And recall here that ln is just a special logarithmic function where the base is e. We still don't know what e is, but we know e is somewhere between 2 and 3. So what are those properties? There's 3 of them, and we'll only need 1 here, but just for completeness, let's look them over. So if we have the ln of a times b, where a and b are both positive, the ln is a logarithmic function, so that's the ln of a plus the ln of b. If we had ln of a divided by b, this is ln of a minus ln of b. And the third property, the one we'll use, is the ln. If you take a to the b, you can move the exponent outside of the logarithmic function. So this is simply b times ln of a. And this is the property we'll use here. But we'll go backwards, right? We have here a multiple of ln of something, so we have b times ln of a. Let us rewrite the limit as h goes to 0 of, now, this is b times ln of a, but b ln of a, we can move the constant multiple in the exponent of a, so this will be the ln of 1 plus h, and then we move the constant multiple 1 over h to the exponent of the argument, so it will be the ln of 1 plus h to the power 1 over h. It's the ln of this expression. And one last step, because ln is continuous, the limit of ln of this will just be ln of the limit. We can move ln outside, because we're asking what happens to ln of this expression as h approaches 0. And we know the answer is 1. So if you look back, the only way ln of something equals 1 is if that something is equal to e. But that's what we have right here. We take the ln of 1 plus h to the exponent 1 over h, and as h approaches 0, this will approach something, but the ln of this expression is equal to 1. If the ln of something equals 1, this quantity has to be e. So this quantity here has to be approaching e as h approaches 0. Once again, because we knew this limit was equal to 1, but the limit is the ln of something, so the only way for this to equal 1 is if the argument here is becoming closer and closer to e as h shrinks to 0. So what does that give us? Well, therefore the limit, this will equal e as h approaches 0 of 1 plus h to the power of 1 over h. This has to be exactly equal to e, because as h shrinks to 0, the ln of the expression we knew was exactly equal to 1. Therefore, as h approaches 0, this has to approach e. So e must equal this limit. And now we're back with a very familiar problem. If we want to estimate this limit, let's just take a very small value of h and we'll have an approximation. So if we take, say, h to be 10 to the minus 6, if you prefer, that's 1 over a million. Now this is very small. That's also, if you want, 0.000001, right? 1, 2, 3, 4, 5. Oops. 1, 2, 3, 4, 5, 6. And now we can plug in this value of h in here by 10 to the negative 6, or 0.000001, and we'll have an approximate value for this function when h is close to 0. So let's compute this. So 1 plus 0.000001 to the exponent 1 divided by 0.000001. And if you compute this with your calculator, you will find approximately a value of 2.71828. And there are other decimal values. They will not be accurate, but at least you will get the first 5 digits accurately. And if you wanted an even better approximation to e, all you have to do is take a value of h even smaller. You could take h to be 0.00000001, use your calculator, plug it in, and you will have an even better approximation to e. And that is how we know that e is approximately 2.71828. Proving that this number is irrational is a lot more challenging, and so we'll leave this aside for the time being.